Good afternoon, guys. This is Dr. Edwards once again. What I want to do now is to talk to you a little bit more about the important terms and ideas in the second part of Chapter 11, the beginning portion of Module 2. I've already given the homework assignment for the second part of Chapter 2. Let me go over some of the boldface phrases and words here, and then we'll work on some of the multiple choice, not the multiple choice, the exercise questions that I've given to you for homework. So we've done the first part of this chapter 11. So I'm going to start with talking about polar molecules, and these are molecules that behave as if they're negative charge at one end and positive charge at the other. Water is an ideal case of a polar molecule. A nonpolar molecule is electrically charged uniformly distributed on the average. The molecule methane is essentially nonpolar. Also, the author says polar liquids dissolve only ionic and polar covalent compounds, whereas nonpolar liquids dissolve only nonpolar covalent compounds. Remember that polar molecules, nonpolar molecules do not mix well. In fact, there's virtually not at all. Such as water and oil do not mix because one is polar, the other is nonpolar. But water and alcohol will mix in almost any proportion because they are both polar. Ionic compounds dissociate, this new word, dissociate, dissociate into free ions when dissolved in water. That's an important feature for what's going to come up next, acids and bases. Ions of a given kind in solution have properties that differ from those of the corresponding neutral substance. Remember, we talk about atoms, molecules, ions, IONS, and assemblies and radicals. Right now, ions then are essentially atoms or groups of atoms that, for whatever reason, have lost some charges or gained some charges. So they are either positive charge or negatively charged. And he goes on to say that an electrolyte is any substance that separates into ions when dissolved in water. So here we go now. Now, acids, bases, and salts. Something miraculously happens when hydrogen loses one of its electrons, lose its outer electron, its only electron, when placed in an aquatic solution, in a watered bath. A solution of acids then in water contains this H+1 ions. Solutions of bases, on the other hand, in water contain this OH-1 ions, and that's hydroxyl ions. Strong acids and bases dissociates completely in solution. This word dissociate, they dissolve into their respective type ions when placed in solution. On the other hand, weak acids and bases only partially dissociate. Now come to this word pH, which is a pattern for identifying the nature of material as being acid or non-acid. So the pH of a substance, the pH of a solution is a measure of its degree of acidity or basicity. The pH of water is 7. And when the pH is less than 7, 6, 5, 4, 3, 1.5, etc., the material is strongly acidic. When the material or substance is greater than 7 8, 9, 10, 10.5, 12. It is base-acidic. So water then, pure water, is neutral. It's neither base nor acidic. It is in between, okay? A neutral solution then is neither acidic nor basic and has a pH of 7. In acid-base neutralization, the hydrogen ion and the hydroxyl ion join to form water. You see here, H2O, 2 hydrogens join with 1 oxygen, effectively produce this water molecule. Now salts then, so acid, bases, and salts. Salts are usually crystalline solids that consist of positive metal ions and negative nonmetal ions. A salt can be formed by neutralizing the acid that contains the appropriate nonmetal ions with the base that contains the appropriate metal ions, and then evaporate the solution to dryness. So I wanted to go over these bold-faced words so that you know what they are and have a good feeling for this portion as we get into acids and bases. Why is the pH of water 7? It is because on the average, 2 molecules out of a billion will dissociate on the average. In a pure water bath, 2 molecules on the average will naturally, spontaneously break up into a hydrogen ion on the one hand and the hydroxyl ion on the other hand. So what we have done, we say 2%. 2% is 2 parts in 100. So then 1 billion is 10 to the 9th, but then 2 parts over 10 to the 7th, then so that exponent 10 to the 7th is where we get the notion that pure water has a pH of 7. So as you add more hydrogen ions into the solution, that pH number decreases and it becomes more acidic. That's right. If you remove more hydrogen ions or add more hydroxyl ions, the material will become more base-acidic and the pH number will increase. Okay, so that's the first part of what I want to talk about. Let me now bring up this portion here on some of these terms, and then we'll see how to look at some of them. Hold on for just one moment. Let me see if I can get this so we can see it. The first is 33. So let me go to 33. Okay. I don't want that. So right here. I'll just go from right here, okay? 33 asks the question, do pure acids in liquid states contain the hydrogen plus 1 ions? If not, what do such acid consist of? And pure acids, then like hydrochloric acid, HCl, does not contain the hydrogen ion. It's important to think about that HCl is covalent bonded. It only liberates the hydrogen ion when placed in water. Hear me again. HCl, pure HCl is covalent bonded, these very strong bonds. And that bond is not broken until it's mixed with water. So that's the only time then that you get the hydroxyl ions. All right. So to answer that question, do pure acids in liquid state contain the hydroxyl ion? The answer is no. And the reason is because it contains covalent bonds. All right, next one. Let's see, 35. Would you expect hydrogen bromide to be a weak or strong acid. Why? I just indicate to you that hydrochloric acid, HCl, is a strong acid, one of the strongest, like sulfuric acid. So HCl, and notice that bromide sits right under chlorine in the periodic table. So you would expect hydrogen bromide to also be a very strong acid. That's number 35. 37, excuse me. What is the difference, in any, between a basic solution and an alkali solution? A basic solution is going to contain the hydroxyl ion, the OH negative 1, whereas an alkali solution is going to contain the +1 ions, whether it's the hydrogen ion or any one of the other alkaline elements. It will be +1. Okay, let's see, what is the next one? Is 39. Which is more strongly acidic, a solution of pH 3 or pH 5? Which is more strongly basic, a solution pH 8 or a pH 10? As we said, as the pH indicator gets smaller, it is a stronger acidic material. So pH 3 indicates a stronger acid than pH 5. But on the other hand, a pH of 10 indicates a stronger base than a pH of 8. Okay. Lastly, justify the statement that water is both a weak acid and a weak base. It is a weak acid or a weak base on the one hand, or it's neither acid nor base on the other hand. It is 6 in one hand, half a dozen in the other. It's the same. It's because water sits right in the middle. So it has as many hydrogen ions as it does hydroxyl ions. So there is no excess of either. Therefore, water presents itself as both a weak acid and a weak base. Obviously, I'm talking about pure water, not contaminated water in any way. These are the exercise questions then that I require for this part of the course. Please go there now. Read all of the concept portions. I have one other video out there also that give material pertaining to this part of Chapter 11. Okay? Have a good day, young people. Go on and get this homework in, okay? And work out the homework for the multiple choice questions. I'm thinking everyone should be able to do those as you read through the material that's available and listen to the videos. If you have any questions, contact me, okay? Have a good day. Bye.